Visual abstract. Characterization of the mechanical properties and microstructure evolution of martensitic steel in repeated tempering cycles. Abstract. The purpose of this study was to understand the behavior of martensitic S30 steel under repeated tempering cycles. The mechanical properties were evaluated by performing tensile test, impact test, hardness test, and wear test was performed on pin-on disc wear setup. The microstructure was observed under axio image observer and scanning electron microscope. The spectrography images were also observed on scanning electron microscope. Introduction. S13 steel is hot work die steel. It possesses high working hardness, better corrosion resistant properties, and hot toughness. Generally, the S13 steel is hardened and triple tempered before its use. The handling temperature is between 980 to 1050 degrees Celsius, and tempering temperature is between 550 to 650 degrees Celsius. Materials and methods. The different specimens prepared for performing tensile test, impact test, and to observe microstructure are shown in figure. Results and discussion. Effect of repeated tempering cycle on mechanical properties. With lower soaking time, the ultimate tensile strength decreases, whereas percentage elongation increases as shown in figure. Effect of repeated tempering cycle on hardness and impact toughness. With the repeated tempering cycle, the hardness drops from 46 HRC to 38 HRC, and Charpy impact test indicates that the variation of impact energy varies within a narrow range. It might be due to the partial dissolution of carbides due to low soaking period during hardening, which lowers the carbide precipitation, and thus there is drop in interfacial energy. Microstructure observation from as soft condition to 4 times repeated tempering cycle by using axio image observer. When the microstructure formed is correlated with the mechanical properties, it can be stated that due to coarser grain size, there are fewer grain boundaries, and mechanical properties found to be low and elongation found to be increased. Microstructure observation from as soft condition to 4 times repeated tempering cycle under scanning electron microscope. It can be stated that the lath martensite morphology formed could be the reason to increase the ultimate tensile strength in single and double tempering conditions. Another important observation made after looking at the surface morphology, that is orientation of laths and mechanical properties, that is ultimate tensile strength, is when the martensite laths are closely arranged, it offers more strength as observed in single and double tempering condition, and later on in third and fourth time tempering condition, precipitation of carbides is visible as well as tempered martensite increases, making the material softer. Carbide size analysis. The carbide size for repeated tempering cycles was analyzed and values are presented in table, which indicates that as the tempering time varies from 2 hours to 8 hours, the carbide coarsening occur along the grain boundaries as well as get precipitated inside the lath of the martensite. Spectrography test. Spectrography images indicate that from single to 4 times tempering condition, the brittle failure indicated by cleavage facet in single tempering shifted to ductile failure as indicated by multiple voids and teary edges in 4 times tempering condition. Wear test. With the repeated tempering cycles, the wear rate varies from 90 to 215 micron, and at double tempering condition, the wear was minimum, which can be attributed to secondary hardening effect, that is precipitation of alloy carbides, increasing strength and offering resistance to wear after double tempering condition. Conclusion. At hardening and double tempering, the mechanical properties found to be superior. Critical radius of carbide and percentage volume of fraction increases from double to triple tempering condition. So by controlling critical radius of carbide, mechanical properties can be controlled. Morphology observation also indicate that the closely packed martensite lath orientation controls the strength without affecting ductility in single and double tempering condition. The ultimate strength variation in successive tempering cycle is around 3.5 to 4.5%. The hardness peaks were not observed at 570 degrees Celsius. Above 550 degrees Celsius, hardness peaks are not observed. With the increase in tempering time from 120 to 480 minutes, the mode of fracture changes from brittle to ductile. Wear rate was minimized at double tempering condition, and thereafter wear rate increases as material becomes softer.